Okay, now we turn our attention to the causes from the energy sector of air pollution and solutions as well. So fossil fuels continue to dominate the global energy mix, even though there's been a lot of attention on low carbon energy sources of energy. The overall share of oil, coal and natural gas in global energy combustion has been remarkably stable over the last 25 years. So these fuels accounted for around 81% of total primary energy use in 1989. That is the exact same percentage as in 2015. Over the period, the share of oil has declined from 37 to 31%, but that of natural gas has risen, and coal increased. Actually, the share of coal increased, and the absolute amount of coal increased an awful lot, from 25% to 28%. And the role of bioenergy has remained steady as well, meeting around 10% of global energy needs. As I've said before, the relationship between fuels and air pollutants is not straightforward. There's different grades and qualities of different types of fuels, and there's different combustion technologies which may remove pollutants or be sources of pollutants at different stages of fuel production, transformation, transportation and use. So, for example, prior to combustion, you can have coal washing, which actually removes pollutants from coal. You can have oil refining, which removes the different fractions of oil. During combustion, higher temperatures, for example, reduce pollution. Some technologies can be used to remove pollutants from the smoke. And post-combustion, like catalytic converters, can be used in cars to capture pollution, to reduce the impact of that. So there's no single level of emissions per unit of a specific fuel, but rather there's a range of emission factors depending on all of these variables. So emission factor is, let's say, the grams of NOx per litre of fuel, or per kilometre that car is driven, or per kilowatt hour of electricity produced. And this number is a lot more certain for CO2. As I said before, it's easier to estimate the climate change impact of fossil fuels than it is to estimate the air pollutant impact. So we more talk about a range of emission factors for air pollutants. Nonetheless, we know that certain fuels play key roles in relation to different types of air pollutants. So both in terms of emissions per unit of fuel consumed and their share of total emissions. So first of all, coal use dominates sulfur dioxide. So that So we get about 10 kilotons, 10,000 tons of SO2 per million tons of oil equivalent when we burn coal. And that accounts for more than half of the energy-related sulfur dioxide emissions, followed by oil some way behind. So you can see here, it's got a high emission factor. Here, this is the emission factor in terms of kilotons per MTOE, million tons of oil equivalent. And the emission factor for coal is about 10. Oil is then around 6, and biomass is much lower, around 2. So coal dominates around half of the total emissions of SO2 come from coal. So this axis here is the share of emissions. So the main determinant of that is coal quality, power plant efficiency, and the control technologies in the power plant or the industrial plant. There's a range of emission factors of SO2 from less than 1 kiloton per MTOE to above 30. So the range can be from very low to very high. So the type of technology, the type of coal that you use very much determines the actual emissions there. So for nitrogen oxides, oil dominates. You can see here that oil dominates for more than half. Nearly 3/4 of NOx emissions come from oil. Next highest is from coal, and the emission factor then is much higher as well. Emissions range from about 1.4 kilotons per MTOE in a petrol car, very low in a petrol car, to more than 50 kilotons per MTOE in a diesel truck. So unregulated diesel in poor quality cars, older vehicles, really have very high NOx emissions. And we won't cover this, but you might be familiar with the Volkswagen scandal back a number of years ago, where it was found that NOx emissions from diesel cars are many times greater than is estimated by tests because of cheating. Catalytic converters can make a big difference here, especially in petrol cars. And then for PM, bioenergy. the dominant source. So the source is mainly traditional biomass cook stoves. Again, the emission factor ranges very, very much from the type of fuel that's being burnt. Can be a wet, young, can be waste, which has a very high PM factor, or it can be, very efficient, dry pellets burned in a very efficient wood stove. Average, we estimate, is around 13 kilotons of PM per M2E is released. There's also, there's a very high share of PM as well, also from coal and oil combustion. So in all cases, natural gas results in much lower emissions, as there's an imperative for safety reasons and to avoid corrosion in the transport system, to remove sulfur and other kind of pollutants as soon as practical after production. So natural gas is certainly the cleanest burning of the fossil fuels, at least. So we go through the fuel quality of different types of fossil fuels. For example, oil, only 1% of oil is used in its crude state. Almost oil that we actually use in transport and heating, electricity, comes from refineries. So crude oil is heated through separate different fractions, and different residues have lighter to heavier fuels. This is a very energy intensive process, oil refining, therefore it produces a lot of SO2 and NOx. Crude oil itself contains between 0.2% and 4% of sulfur, depending on where it comes from, with that heavier oil being much more kind of sulfur intensive. And removing sulfur from oil products is actually part of the refining process, and that process is typically regulated by governments. So governments will regulate on the sulfur content of fuels. Typically regulations in developed countries can be as tight as 10 parts per million, and as I said before, fuel oils, which are used in shipping, in maritime shipping, can have the highest sulfur, up to 3.5% of fuels. That's unregulated on the high seas, I suppose. And oil is mainly used in the transport sector. Natural gas doesn't go through the same refining process as oil, but it is nevertheless treated in gas processing plants also to remove sulfur in liquids. And the naturally occurring sulfur in gas can range from close to 0 to as high as 20 to 30%, and even higher in some cases. But as I said, it is typically removed. The next slide here, we have mandated sulfur levels in diesel transport fuels as of 2016. Here, different countries, as I said, have maximum diesel fuel sulfur levels in terms of parts per million. And you can see that in OECD countries, in Europe, high income countries typically have much more stringent regulations, with parts of Africa and Asia having very, very lax. So there can be a much higher share of sulfur in diesel in these countries, which obviously creates big problems in urban areas. Stationary sources of air pollution, the main source there from the energy sector is power generation. So coal dominates power generation worldwide. 40% of electricity comes from coal, and that sector is responsible for around a third of global sulfur dioxide, nearly 27 million tons of sulfur dioxide, 1/3 of the global total. And this actually makes a small but significant contribution to nitrogen oxide. About 14% of NOx emissions also comes from power generation, and particulate matter, around 5% of global PM2.5, comes from power plants. Different types and qualities of fuel, the types of power plant, whether they can include pollution mitigation technologies, locations, smokestack, chimney height, all have a big influence on the power plant pollution types and their impacts. Similar to the power generation industry, accounts for a large share of SO2, around half of SO2 and 30% of NOx and PM. And again, the source fuel, the sulfur and nitrogen NOx contents of the fuel and operating conditions are crucial determinants. There has been a good decoupling of industry pollution and activity because of regulation, like strong environmental regulations, especially in the 70s and 80s, which became standard in all regions, which has had a big impact on industry and stationary sources. There are a number of emission control options from stationary sources. Here, for example, are a number of emissions control systems in power plants. So that ranges from, at the start, the type of fuel that can be used. So if it's a coal-fired power plant, you can use low sulfur coal, or blending coal with low sulfur coal. So that's coal which naturally has low sulfur or which has been cleaned. It can have mercury controls, which are enhanced particulate controls, or these different injection technologies which reduce mercury emissions. NOx control, the combustion chamber can be more efficient, which reduces NOx emissions. Different types of burners which are attuned to lowering NOx emissions. Then post-combustion, you can have catalytic reduction. That's like the catalytic control on your car, which removes NOx emissions from the exhaust emissions. Particulate control, then, that's reducing PM, particulate matter. You can have basically filters and electrostatic control options, which remove particulates from the exhaust. Flue gas desulfurization, that is removing sulfur from the flue gases, including literally spraying water to reduce the sulfur, and then removing that water, and then these different integrated systems which have the same effect. Here are some mitigation options from the stationary sources here, and the efficiency. So some of these options, for example, filtration of PM 2.5 can remove over 99% of the pollutant. Some, can have 20 to 30% efficiency at reducing, say, NOx emissions. So basically stacking all these up reduces efficiency as much as possible, reduces pollutants as much as possible. Next, looking at mobile sources, which basically means the transport sector. So transport is responsible for around half of NOx emissions, around 56 million tonnes in 2015. And transport is also an important source of particulate matter, around 10% of energy-related PM 2.5. And road transport is by far the largest source of the sector's NOx and primary PM 2.5 emissions. And navigation accounts for a lot of SO2 because the fuel content is unregulated largely. And road vehicles are driven in populated areas, so because the emissions are close to the population centres, the impact is much higher. Because of the large engine size, use and reliance on vehicles, diesel fuels, heavy-duty vehicles, HDVs or HGVs, account for a very large share of NOx emissions, far greater than their share of the global vehicle stock. And what really matters for this sector, for these mobile sources, is regulation, is how vehicles and their pollutants are regulated. This is a table of emissions and fuel sulfur standards for the transport sector in many world regions. And remember, road transport activity is growing very strongly. It grew by about 1/4 in the past decade, but NOx and PM emissions grew by 5% and fell by 6% respectively. So basically, there is happening a decoupling of road activity and pollutant emissions. However, there has been a sort of a famous failure of EU regulations called the Euro standards to effectively reduce NOx emissions from light-duty vehicles in the world because of this gaming of the testing system, which has led to these scandals that you know as the Volkswagen scandal. So here we go through different Euro standards. Here the Euro standards there were introduced by the European Union and have been applied to many other countries actually as their standard as well. But if you see here, Europe for light duty vehicles is on Euro 6, so the 6th generation of standards. Here South Africa, Indonesia, other developing countries are still on Euro 2, which are much less stringent. It's not just air quality standards like this which have had an impact on local air quality, but also better management of transport use, such as better transport planning, public transport incentives. Many countries have started to ban cars from the centre of cities and towns, and to have low air pollution zones where only cars above certain standards can actually enter. Of course, EVs, there are for electric vehicles, there is no combustion in the EV. There is some at the power generation source, but EVs don't create the same level of air pollution like this from NOx, PM, and sulfur, because there is no combustion in the car. However, EVs actually do create some abrasion levels of PM. You know, if the tires and the road are abrasive, and and that creates some level of PM 2.5. So one interesting factor about these vehicle test standards is that there's a growing gap between the real world driving conditions emissions and those from the vehicle tests. So here are the Euro 3 standards from the year 2000, and now we're under the Euro 6 and later standards, 2014. And the emissions limit is the blue area, and the pink, this is from diesel cars, which are the biggest source of NOx emissions, are the emissions measured under real world driving conditions. And you can see that, okay, they were around double. The real world driving emissions were around double in 2000, but they're many times greater, 5 times greater than the standard now. So basically, whereas the Euro standards have gotten progressively more stringent, there's a huge growing gap between the actual performance and the test standard. Next, we look at buildings. Energy use in buildings is responsible for more than half of all PM 2.5 emissions, mainly due to the lack of electricity and clean cooking access in developing countries. Here's a kerosene lamp. Also, candles are used frequently as a source of lighting. When there's no electricity access, sometimes there is small diesel or petrol generators which are used to provide electricity, which are also sources of air pollution. But by far the biggest source here is clean cooking. So billions of people live in homes which don't have modern clean energy sources, that has bigger health burdens in terms of carrying time burdens with the amount of time it takes to cook on a source like this is very significant, takes away from learning opportunities and so on. So finally, we go through some interesting factors around air pollution in Ireland. There was a big EPA report in 2018 on air quality in Ireland, and it's been found that Dublin air pollution has fairly frequently breached EU limits. Poor air quality prematurely kills more than 1,100. Some estimates are over 1,500 people in Ireland every year because of poor quality standards. Now, the images that are often given are of cars like this, but actually the main health burden in terms of premature deaths is mainly from particulate matter, which comes from burning coal, peat, and biomass in homes. So you'll see in especially smoky coal areas, which haven't banned smoky coal, you'll see a haze in the evening. You can taste it in the air, and this produces this very fine particulate matter that penetrates deep into the lungs and has a very bad health impact, especially for very young people and very old people. Ireland has a national ambient air quality network, and you can access those monitors online if you're interested, that the EPA runs. This is the Air Quality Monitoring Network in 2018. You can see some sites in Cork. And this measures different particulate matter, PM 2.5 and PM 10, NOx emissions, sulfur, ozone, carbon monoxide, and others, to test when Ireland different areas are exceeding the EU and the WHO guideline values. If you're interested there, you can have a look there. And in Ireland, traditionally, we have a focus on measurements, the quality of air we breathe. However, there is more recently a need to focus on more local air quality information. So the EPA is developing general ambient air quality monitoring at urban and regional scales. And also it's interesting this week that the Met Éireann, I believe, are going to start introducing air quality forecasts. Now in Ireland, we actually have fairly good quality air relative to many other countries, but in localized areas, especially in these cold, still winter nights, you can get very high levels of air pollution. Now we can look at some monitoring sites in Ireland and globally. There's a number of different networks and websites. So for example, here is the EPA site, airquality.ie, which will take you to the almost real-time monitoring of air quality in different regions in Ireland. If we can, for example, look here in Tipperary town, we can see the latest PM10, PM2.5. In some areas we can see, so air quality looks pretty good. I'm here in a, fairly cold winter evening. People haven't started lighting the fires yet. But if we look as well, here is a different air quality monitoring site. This is Purple Air, and these are this is a network of kind of low cost air quality monitoring sites, and these have gained interest recently because they've shown in some areas in Cork the air quality can be worse than the kind of worst places in India and the US. But here you can zoom out and look at the air quality across the world. So here we've got, my internet is pretty slow. Oh dear. There we go. Europe, parts of Europe looking very bad. And zooming out even more, I think that air quality network is mainly in, yeah, there we go. India is very bad. Can be terrible. And here here's another air quality index called wacky.info. Again, taking real-time information. You can see that many of the sites in countries in Asia are off the charts. They're very unhealthy, and you can see that PM going up and down. In Ireland, we have relatively good quality air because we're not industrialized, high regulation, things like that, but a lot more to do as well. So in Ireland, again, the main sources of PM are solid fuel burning. Why is solid fuel burning so bad for air quality? It's because burning solid fuels in stoves, especially in open fires, is very inefficient. Not all the solid fuel is actually fully burned, and those unburned particles leave the fireplace by the stove or by the chimney. So there actually is also air pollution indoors from the fire, not just from the chimney, into the room, and that causes both indoor and outdoor air pollution. And there's different EPA sources that regulate that.